In this video, we are going to take a bit of a sidetrack to talk about conventional current. You might have watched the other videos so far and been thinking, wait a minute, you keep drawing current as flowing from positive to negative, but we know that in a metal conductor, which is what we have in circuits, they're made out of metal wires, the charge carriers are electrons and they flow from negative to positive. So why are you drawing current like that instead of like this? And you might not be very happy with the answer, but as the name conventional current implies, the answer is pretty much just because that is convention. As usual, there is an XKCD for that might explain this a little better, so go check out xkcd.com, number 567. But the short version is basically that scientists established this convention for positive and negative in electrical currents and charges before we fully understood what electrons were. So they didn't actually understand that in the case of a circuit with metal conductors like this, that electrons were the things that were actually moving. And they thought, okay, we're going to define current as flowing from positive to negative, and then later realized, oh wait, electrons, which we have already assigned to have negative charge, are these things that are actually moving in the opposite direction. So mathematically, it all works out the same. It just kind of trips some people up that the physical electrons are actually moving in the opposite direction. You might hear physicists talking about the movement of positively charged holes, which are sort of not actually a proton or a positive particle, but the absence of an electron, or a gap where there's a missing electron, therefore that area has a positive charge. There are also cases where moving charge carriers might actually be positive. For example, if you look at what's going on inside a battery, I am not a chemist, so can't explain this very well, but you have ions and things flowing around inside the battery or in a chemical reaction where some of the things moving around might actually have positive charges. Another example is a particle accelerator, where you have some beam of protons or positively charged particles moving around. There you actually have positive charge carriers instead of negative carriers. So again, it's confusing when you're taking a circuits class because 99.99% of the time we are working with circuits with metal conductors where the charge carrier is a negative electron. But there are these other scenarios where you can actually have positive charge carriers, and mathematically, for the things we're doing, everything works out the same. So we've seen so far we have Ohm's law, and we have the power equation, and it doesn't really make a difference which way we draw the arrow for current when we're just using these equations. Now, those directions are going to matter in the future when we get to more complex circuits, which we've hinted at. For example, with multiple resistors, where maybe it's not always immediately clear which way current is flowing. That is where it's going to become important to stick with this convention that current flows from positive to negative. So we'll see that more in the next few videos in this series, but again, for now, there's just kind of historical reasons for this. Go check out the XKCD if you haven't seen that before. And if you don't like it, you're going to have to get over it and learn to accept it, because this is the convention I'm going to be using throughout this course.